This is a lesson on what happens to a loop of wire as you drag it into a magnetic field. We're going to take a look at what happens to current in the wire, how it is induced, and also magnetic force that is on the wire as the wire moves into this region of magnetic field. So for understanding current, the key equation is Faraday's law, which is that the EMF will be negative change in flux over change in time. It's important to remember what flux is. This was something that was giving students some trouble in class. Flux is the amount of magnetic field enclosed by the wire. So outside the wire doesn't matter. Inside, right now, we're starting to see some magnetic field inside the loop. That means the flux coming at us is increasing. So we expect an EMF to be induced. As far as current goes, well, we know that EMF can basically be used like a potential difference. It's measured in volts. So we can plug into Ohm's law to figure out magnitudes of current. But that's not what we're interested here. We're really just trying to think about what direction that current might be in. The most important thing for helping us with that is this negative sign. This negative sign is sometimes called Lenz's law. And it's kind of part of a general principle in nature that sometimes when you have a balance, if you upset that balance, nature shifts to oppose you. Kind of like in chemistry. If you have an equilibrium and you start adding too many products, it might shift back to make more reactants. So what's happening here? As our loop of wire moves into this region of outward magnetic field, there is outward flux increasing. And what the wire then is going to do, the charges in it are going to experience forces to have a current to oppose that change in flux. So what we're going to see is we're going to see an attempt by the wire to make inward flux to try to cancel out the outward force that's being added to it. So what direction will that mean the current's going to be in? If the wire is trying to make inward flux, we basically have to take our hand, do this right hand rule, remembering the thumb is the direction of current and the fingers are curling in concentric circles for the magnetic field. If we want inward flux, that looks like this. My fingers are going into the wire in the middle and coming out on top of it. So that only works if the current is pointing in the direction of my thumb, which is to the right in this case. So that means our current is actually in this direction. So that will induce a current that goes in this direction, and because it's a closed loop, that current will be on all sides. So we end up with a clockwise current under these conditions. What happens when our loop is fixing to leave? Well, it's probably spent a whole lot of time in our field, in which case it had all outward flux. At that time, there wouldn't be any current induced because there wouldn't be any sort of change in flux. You only get an EMF and a current if the flux is changing. So when you're in the field and you're entirely in the field, you don't see either of those. But as we leave the field, now we had a bunch of outward flux. As we leave, that outward flux is disappearing. So what's the nature going to do to oppose our change? Nature is going to try to add outward flux back in. It's going to do that by inducing a current in the opposite direction because my fingers inside are pointing out now. So now we'll get this situation. So hopefully that helps us understand currents as a wire enters a perpendicular magnetic field and then leaves it. How about forces? Well, let's just look at it in this situation when it's entering. In this case, the relevant equation is this one. And since the magnetic field is perpendicular to the loop, it's just this. So let's try to figure out what direction there are on different sides of our loop as it's entering. So you just are going to use this right-hand rule in this case. And it's the same right-hand rule we would use for charges moving through space. This is velocity, this is field, and this is force. Now, which direction are the charges moving? They're moving in the direction of the current, as long as we say that positive charges are the things that are actually moving through the wire. So let's start with this current here. Got my thumb pointed in the direction of, or excuse me, my index finger pointed in the direction of current. I'm going to curl my fingers outward because that's the direction of the field. And that means that this side here is starting to experience a force in this direction. And it's just because of essentially this part that's entering. So really I should have drawn it up there, but I was worried it was going to get too confusing. I could play the same game here. There's current, there's field. So this side's going to experience a force in the opposite direction. So effectively, whatever forces these two sides experience, they're going to cancel each other out. This side ain't going to experience a force because it's not in the field. So it all comes down to what direction is this side. So velocity in the direction of field, you can see how the right-hand rule is awkward. I'm getting a force in that direction. So basically, I'm going to get a force that's opposing my velocity. If I'm not dragging this through here, I'm going to have an acceleration to slow this down. I hope that helped with this. If you've got an unplugged power cord or a charger or something like that, you can make a loop and try these out. I think that will help better. Good luck. Let me know if you need help.